So another type of motion we want to consider is relative motion, where things move relative to each other. Okay, so to describe this, what we usually need to do is we need to pick a reference point, something to represent kind of stationary motion, what everything's moving with respect to. So we choose a reference. And typically this reference that we're going to choose is usually going to be Earth, but it can be whatever we want. We can choose whatever reference point we want. In 1D, this is pretty clear. This is pretty straightforward. So let's say I have a train. And I have that train, and that train has a velocity. So the velocity of this train relative to the Earth, and I'm going to use these subscripts to represent that, train relative to Earth is equal to 10 meters per second in the I hat direction. Now let's say that there's some person on the train and they are walking. So I can take this person and I can figure out the velocity of the person relative to the train is going to be equal to -2 meters per second. Maybe I'm walking backwards towards the food cart to get a nice bag of gummy bears that's ridiculously overpriced. So now, in relative motion, we would ask the question, okay, I'm going to use Earth as my reference point. So what is the velocity of the person relative to the Earth? And here we can see why I chose the subscripts that I did. What I can do is I can imagine that these middle variables, these reference points that are in common between the train and the person, that they're going to cancel each other out. So I can take the velocity of the person relative to the train, and I can add on the velocity of the train relative to the Earth. I can combine these velocities. They're relative motion. I imagine that these inner variables cancel each other out. So this t goes away and this t goes away, and I'm left with just the p and the e. So the velocity of the person relative to the Earth. So let's write out this explicitly. V of p e, person relative to the Earth, is v of the person relative to the train, -2 meters per second in the I hat direction, plus the velocity of the train relative to the Earth, 10 meters per second in the I hat direction. I combine these together and I get my relative motion is 8 meters per second in the I hat direction. So in one dimension, this is pretty straightforward. What does it look like in 2 dimensions? So let's look at this problem. Let's look at a ship that set sail from Rotterdam, and we're heading due north at 7 meters per second relative to the water. And then the local ocean current is 1.5 meters per second in a direction that's 40 degrees north of east. What is the velocity of the ship relative to the Earth? Okay, so I'm given these numbers. Let's write down what these numbers actually mean. I have the velocity of the ship, but that's relative to the water. So we're going to say ship relative to water is the velocity, and that's going to be 7.00 meters per second. I'm traveling due north, so I'm going to assume that that's entirely in the j hat direction. So this is my velocity. I'm going entirely north in the j hat direction, 7 meters per second. Now the local ocean current, the water, is 1.5 meters per second in a direction that's 40 degrees north of east. So what does that look like? Okay, so I need to draw a coordinate axis so that I can see what this actually looks like. So there's my coordinate grid. I assume my north is kind of the j hat direction, my east is kind of the I hat direction. I'm going 40 degrees north of east. So north of east is going to be north, moving north of this east direction. So that's got to be 40 degrees right there. And this is my vector. And I know how big that vector is. That velocity is equal to 1.5 meters per second. So the velocity of this water relative to the Earth is going to be 1.5 meters per second at 40 degrees north of east. And what we should be pretty used to by now, anytime we have something move at an angle, we break it into components. We need to break it into the x and y pieces of this. So we have some little bit of this motion that's moving in the x direction. So that's the velocity of the water relative to the Earth in the x direction. And we have some velocity of this water relative to the Earth in the y direction. And I can see this right triangle here that I've drawn, and we should be good at picking this out by now. The velocities are going to be component analysis of this. So to get v of water relative to the Earth in the x direction. That is the adjacent side of that triangle. So that's going to be 1.5 times the cosine of 40 degrees in the I-hat direction. So we multiply this out and we see that that's 1.15 meters per second in the I-hat direction. Then we have V of water relative to the Earth in the y direction, traveling north, is 1.5 times the opposite side of that triangle, right? There's the 40 degrees. The VWEY is on the far side of the triangle, so that has to be the sine of the angle times the sine of the 40, and that's going to be going entirely in the j-hat direction. So we multiply this out, and we find VWE in the y direction is 0.96 meters per second in the j-hat direction. So how do I find what the velocity of this ship is relative to the Earth? Well, I can use my vector notation. Velocity of this ship relative to the Earth has to be equal to the velocity of the ship relative to the water plus the velocity of the water relative to the Earth. And that's in vector form. And because this is in vector form, I need to add it up in vector format. So velocity of the ship relative to the Earth is going to be the ship relative to the water, 7.00 meters per second in the j-hat direction, plus the velocity of the water relative to the Earth, which is the combination of the two of these, both in the I and j direction. So that's got to be plus 1.15 meters per second in the I-hat direction, plus 0.96 meters per second in the j-hat direction. So there we have a nice equation that represents the velocity of the ship relative to the Earth. There are some terms that I can combine here. So let's combine the like terms, velocity of the ship relative to the Earth. Combine all the I-hats. There's only one of them, 1.15 meters per second in the I-hat direction. And combine the j-hats, plus 7 in the j-hat plus 0.96 in the j-hat. So I add those together and I get 7.96 meters per second in the j-hat direction. So there is a nice little vector that represents this. So let's draw this out and see what it actually looks like. We have our coordinate grid. I have some little bit of this going in the x direction, so we have v in the x, and we have some little bit going in the y direction, v in the y. To find the total v, I need to take this and find the hypotenuse, which is the square root of the sum of the squares. So v has to be equal to the square root of 1.15 squared plus 7.96 squared. So v of the ship relative to the Earth, when I take the square root of the sum of the squares, is 8.04 meters per second. Now what's the angle that this is acting at? So here's my angle. I can pick any kind of triangle that I want inside of this. I'm going to pick tangent. I just tend to pick tangent because it's the easiest in my brain. So tangent of theta is the opposite side over the adjacent side. Opposite side is 7.96 divided by the adjacent side, 1.15. To get the angle theta, I take the arctangent of both sides. So the arctangent of 7.96 divided by 1.15 will give me my theta. That theta is equal to 81.8 degrees. So that's going to be 81.8 degrees north of east. Or we could also write this as above the x-axis. Either one of those will work for me just fine. So this is combining relative motion in two dimensions.